the Physics 2A video lecture, Physics 2A video lecture 4. And we'll pick up where we left off. We're talking about motion, and we're talking about the science of kinematics, which is just a fancy word for the science of motion. So kinematics, and we're going to go through that and come back to the free fall idea and make our way, I think, quite a ways today. Good, so kinematics, and I had already written down these 4 concepts: position, and I'll write them down here: position, displacement, velocity, and acceleration. So position, displacement, velocity, acceleration. And we had done these first 3. Let's look at them again before we tackle the acceleration. So position, x, the units are meters. You're on the number line. It doesn't have to be a horizontal line, but we are working in 1 dimension. It could just as well be vertical. 0, 1, 2, and you've got your location there somewhere. The displacement is the change of the position from one point to another. So displacement we call delta x. X, I can sometimes write x minus x0, or I can write x final minus x initial. The point is there are 2 places, and the difference between those positions is the displacement. Units are also in meters. Then we have velocity. Velocity v is delta x divided by delta t. Putting the delta on both of those just for symmetry. The units of v, we do the square bracket, are length per time, or meters per second. And we ended with a graph of x as a function of time, a straight line graph. And if you have x as a function of time in a straight line graph, that means that you're looking at x equals x0 plus v0 times t. Right? So you're graphing, and the intercept is your x0, and the slope is your v0. So we're indicating that it's constant. We have a constant slope. And t here is your independent variable. You're on the horizontal axis. And I think we ended with the idea that if the slope is greater, so if the curve is steeper, like my ruler is now, that corresponds to a larger value of the slope, and that's a higher speed or a higher velocity. Good. I can add to this something I had to mention the other day, and that is the idea of instantaneous velocity. Instantaneous velocity. And that is v equals a limit as delta t goes to 0 of this same difference quotient, delta x over delta t. So if you had calculus, you saw some limits. What that really means is, for a very short time, you have a certain speed. If you were in your car and you're driving and the speedometer says 60 miles an hour, put your foot in the gas, a few seconds later it is 70 miles an hour, okay? So your instantaneous velocity was 60 at the beginning, and then it was 61, 2, 3, 4, 5. Eventually it was 70. Okay? But of course, in this class, it's not miles per hour, it's meters per second. But it's always length over time. Good, so the instantaneous velocity, little sub-discussion there. But now we get to the last in our list here, acceleration. So acceleration is going to be the letter A is equal to delta v divided by delta t. So it's the change in velocity over time. What are the units of acceleration? Meters per second divided by seconds, so we say meters per second squared. Okay, the units of acceleration are meters per second squared. We're familiar with accelerations in life because we even call the pedal on the car that you press the accelerator. Okay, it changes our velocity, changes our speed in a certain amount of time. Nonetheless, this concept is trickier and not as intuitive as position and velocity, but very crucial for what's going to follow. So these are the concepts. We have position, displacement, velocity, acceleration. And everything we do to characterize motion will be in terms of these concepts here. So the whole science of motion is dealt with by this set of concepts. You need lengths and times, meters and seconds. Okay. Now, before I move on to talk about free fall again, let's go ahead and do the graph of this thing as well. So we have A equals B minus V0. You could say divided by T minus T0. That's what this expression here would be if I wrote it out. And I'm going to go ahead and ignore the T0. Suppose the T0 is equal to 0. And solve for V. What do I get? I'm cross multiplying, so I'm going to have A times T, and I'm bringing the V0 over to the other side as well. And I get V equals V0 plus A times T. And let's go ahead and write when acceleration is constant. And I'm going to graph this. A new set of letters, but just as we had x of t up here, here we're going to graph v as a function of t. And if the acceleration is constant, then here's our independent variable. Here's our intercept. So the intercept is called the initial velocity. And again, we have an equation of a straight line. So under constant acceleration, the velocity increases linearly. So we do quite a bit of graphing, especially in our lab. Traditionally, we do quite a bit of graphing in the lab, and I do a lot of graphs on the board just to illustrate concepts. So the constant acceleration case is going to be a very important one in what follows. And so this graph is also going to play a role. So I'm going to put a note under here. Suppose we have a velocity at some time a little bit later than time equals 0. This is, of course, t equals 0. And the velocities have grown linearly. That means the average velocity in this particular case is just the midpoint on the curve. Right? Just the midpoint on the curve. So I'm going to put this as a note for future reference. And this is the constant acceleration case. V average is equal to V plus V0 divided by 2. And yeah, let's write V average. Average velocity for this particular case, constant acceleration. Good. So by the way, when you're taking your notes, leave a lot of space. Okay, leave a lot of space. You can put little comments in there that way. And definitely this kind of implication you want to go over yourself and make sure you're able to go from here to here algebraically. The more practice you get on these things, the better. Okay, so there's our acceleration. We have motion with constant velocity, that was this graph here. We have velocities and constant acceleration. So these two graphs look the same, but they're actually very different types of motion. Constant velocity versus constant acceleration. And I think I'll bring a demonstration in. We have a frictionless air track in this lecture hall, but I'm working with a fixed camera, one take, no edit. So what I'll do is bring a track onto the table here. Okay, this is a track, and I can run cars on here with relatively little friction. Okay, here we go. Got to make sure the thing is level, and then we'll do a couple of little demos. Yeah, so motion on a frictionless track, the idea is you just give this thing a push and it keeps rolling, and that's motion with constant velocity. We could even so if this thing's level, then we'll have constant velocity. That's not a bad approximation. Okay, just give it a push, and it neither picks up speed nor slows down. Okay. Now, on the other hand, constant acceleration, the classic example is the inclined plane. Okay. So I put this on an inclined plane and say, marks, get set, go. Maybe I should give this a little more elevation just to make sure. There we go. Now we're going to roll downhill, and you see it's picking up speed. Starts out moving very slowly, and in the first second, distance, next one, much a greater distance. Okay. So if you were to count this, say you had a stopwatch, say 1001, 1002, 1003, and after 1 second, after 2 seconds, after 3 seconds, it's always a greater distance. So that's the accelerated motion. And that's what we're going to study now. Now, what Galileo did with free fall, remember we started talking about free fall. I brought a tennis ball along so I can have something to throw around. It's always a good demo if you got a tennis ball. So Galileo was trying to understand free fall. We talked about the hammer and the feather. We get rid of the friction. So as you're dropping a brick, that's going to have very little friction. It's going to fall in a certain manner. And as much as you want to study it this way, you can't see what's going on. The action's over too fast. Galileo did this inclined plane, slowed it down, and if you want to study it even closer, you can slow the action down even more, but it's still accelerating. So we have this idea that the same behavior in the free fall is happening during the inclined plane. It's just being slowed down so you can study it easier. And he was actually able to come up with the law of free fall using an inclined plane and then testing it with dropped objects. Okay. So I'm going to do a little more demonstration along those lines. Okay, so we're talking about free fall. So let's go ahead and write that down. Free fall. And the first thing we saw was you eliminate friction and everything falls the same. So eliminate friction putting the feather on the book like I did last time. Eliminate friction. All objects fall the same. Okay. So that still doesn't tell us what's the law. How do we express that in terms of position, displacement, velocity, acceleration? Well, we can easily say that the motion is accelerated. I just showed you, you release something from rest on the free fall, or you release it from rest on the incline here, and it's picking up speed. The velocity is changing. Where's our concept, right? The velocity is changing, so there's acceleration. So it is accelerated, but then there is one more step, and that is to very carefully measure the distance for each increment of time. And you find, you count 1 and you've gone this far, but it's moving, so you count 2. So 1, 2, and it's done an increased distance. So it was a greater distance, a smaller distance. The third one's going to be even greater still. Okay, so I have an interesting little device that I'm going to demonstrate. You guys can do this at home, which will make it all worth it. Let me get rid of this thing for now. Okay, I want to demonstrate what's called a drop chord. And this is something you guys can try at home. Always worth it. So the drop chord has some kind of sounding board. In this case, it's going to be our tabletop. And then you have a string. You anchor the string somehow. Well, actually, you don't anchor it. I'll show you in a moment. Yeah, you give some ground level, and then you mount some little objects that can make a clicking noise. So you'll notice these are increasing distances, but we're going to clip them to the string in such a way that as they fall, they give an even rhythm. So the stopwatch had not yet been invented in Galileo's time, but everybody is born with a sense of rhythm, so you can hear the even rhythm, and that will tell you your increments of time, 1, 2, 3, 4. So I usually do this with a much longer string, but since I'm limited to everything above the table here, I'm just going to use a shorter section of the string. And I'll construct our drop chord. What I was about to call the anchor is just a pen here. And since I know the answer, I have to be able to measure out the proper lengths. And the clips that I have, and you guys can have something like this. You can use paper clips. I have these little clips here. So I have to clip them to the string in certain lengths, certain distances that only I know, although you're going to know them too soon enough. And I think this shorter version will still work. Okay. We can even do one more here, I think. Okay. We have another one. Yeah. Double this back here. Okay, here's my plan. So my drop chord, stand on something. Okay, good. You go get something to stand on, that's well worth it. Actually didn't have to go that far. Okay, here's a stool I can stand on. So, the idea is to drop this thing. And what you guys are doing is just listening carefully. Let's hope the microphone picks this up. Less than overwhelming. Let's try it on this sounding board right here. Once more with feeling. Okay, this will make it a little more of a ringing sound. Like I said, you guys try this at home. Once you have the concept, you want to hear 5 even beats. Okay, I'm declaring victory. I heard them. 1, 2, 3, 4, 5. And we'll see how this comes out on the tape. But now that I've done the drop chord, I'm going to explain to you what I just did. Carefully, and that will actually lead to the next mathematical development. Okay. Check this up. And get back to mathematics. Okay, what does that have to do with our mathematical development? First of all, we've got the soundboard again, the drop chord here, so we can illustrate this. These are just clips, and there is an increasing distance there. Okay? So when I release this, the first one strikes, the second one strikes, the third one strikes, in even rhythm, 1, 2, 3, 4. So we're going to put a data table here. We've done the data, and we have time, we have the distance fallen. And the time when I released it was 0, so we had 0, 1, 2, 3, 4, 5 units of time. The main thing is that they were even. That's what the rhythm told us. Now what about the distance fallen? I didn't tell you, but I knew the answer. At rest, of course, it hadn't fallen at all. I then had 5 centimeters. We're going to leave a third column here. I had 5 centimeters, 20 centimeters, 45 centimeters, 80 centimeters, and 125 centimeters. So we can't yet see the pattern there necessarily, but let's divide them all by 5. Then I have 1, 4, 9, 16, and 25. Okay. If I divide these 5 centimeters by 5, I get 1, and that's my unit of length. And then I have 4 units of length, 9, 16, and 25. And now the law is practically staring us in the face. You could say the distance fallen is like the time squared, because, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. And that is actually the law. So let's send this up here. And actually these definitions are good, so we'll leave them up. Leave these definitions up right now. Keep working under here. So what we have is distance fallen is proportional to the time squared to the elapsed time squared. That's the law that we have in our data table here. I could also say d for distance fallen is proportional to time squared. The reason I say proportional is because it depends on the choice of units, right? I had unknown units of time here. I had centimeters here, but when I divided by 5, I just had a unit of length 1, 4, 9, 16, 25. So it's a proportionality. There would be a constant there if you choose the appropriate units. Good, we've got distance proportional to time squared, and that means we have distance over time squared is equal to constant. Okay. The distance over time squared, that ratio is constant, but what are the units of distance over time squared? Let's do the square bracket here, and what do we get? We get meters per second squared, and those are the units of acceleration. So we already knew the free fall is accelerated motion. Now we know it is motion with constant acceleration. Okay? So that's the big takeaway here that we learned, and I'll write that down over here. Free fall is motion with constant acceleration. And this allows us to just completely determine the kinematics of constant acceleration motion. So free fall is motion with constant acceleration. I'll underline that, constant acceleration. Acceleration. Good. Free fall is motion with constant acceleration. And what we're going to do now is use our formalism with constant acceleration, and we'll get the famous kinematic formulas. So this is one place in physics where we actually get out a law of nature and an exact formalism just with what we did here, just with what we did together in class. So by the way, before I go on, this drop chord idea, you guys should try it. Try it at home. You can also make longer ones. Usually I make it twice as long, and I have to stand up here on the table and I can drop it down to the floor, but we didn't have as much room here. So I went with less than 1.5 meters of string, but it's these different distances. Now that I have it on the table, I'll illustrate it one more time. It is 1 unit starting from the bottom here, then it's 4 units, then it's 9, 16, 25. What would the next one be? If you have a longer string, stand on a ladder, you'd go 36, 49. So if you just choose a unit of length, I chose 5 centimeters, and then you go with it. Okay, so yeah, that drop chord, and it's the same thing that can be done on an incline. So what Galileo did was he was rolling things down an incline of hardwood, and he had, say, a marble, a steel ball, a marble or something, and he, in the groove, he would install little things that would click, okay, that he could move back and forth. And so he would get the click, 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 click in even time, and he could just adjust those distances till his ear told him that it was perfect. Now, what I did was I already know the answer, and I didn't have all afternoon, but you could actually discover the law systematically if you had enough time. You would just keep adjusting, your ear would finally tell you it's perfect, and then you would do the measurement and you would discover this time squared relation. Good. So that was a first when it was done by Galileo. Okay, so now we're doing motion with constant acceleration, so we're going to call this kinematics with acceleration equals constant. And what we do is we just take our definitions and apply them, in fact. So let's see what we have here. We have average velocity is equal to x minus x0 over t. That's our delta x over t, right? And average velocity. And I'm calling average velocity with the v over here. Well, we're going to solve. We'll get x equals x0 plus v average times t. And the second definition we're going to put in is when acceleration equals constant, we have v we have acceleration equals v plus, no, we have v average, sorry. We have v average. Actually, let's do this in two steps. So we have v equals v0 plus acceleration times t. Okay. That was the second equation. That was the one we graphed as a straight line. And the third equation was the property of the straight line that I had given you guys in terms of the average. It's the average speed, and that was v average equals v plus v0 divided by t. Okay. So this is an application of these definitions essentially. Constant acceleration, this is the one that we graphed. This was the property of that graph. And now we're just going to plug them all in. So, I'll mark underneath here. We're going to plug them into each other and see what comes out. Okay, so what we'll do is x equals x0 plus v average t, but this time we're going to keep going. We have equals x0 plus, okay, here's a mistake. That was divided by 2, not divided by t, divided by 2. Okay. x0 plus v plus v0 divided by 2 times t. And finally, we've got x0 plus, I'm going to write this v in the parentheses, v0 plus at plus v0 divided by 2 times t. So all we have to do is simplify this thing. You see we're going to have 2v0 divided by 2, and then at divided by 2, and that all multiplied by t. So without further ado, we have x equals x0 plus v0t, right? These two divided by 2 times t, plus 1/2 acceleration t squared. Okay. This is the famous distance times squared law with a box around it. This is what we're going to see so often you'll certainly memorize it without even trying. That's a good time to make the point. We don't have to memorize things in physics, we just repeat them so often that they just become ingrained. And you'll see that that's what happens with these formulas. You write them down often and reflect on them. Right now we're just getting them here. We're just going to repeat this one that we had out of our definitions for constant acceleration. There is a third equation. I'll number these 1, 2, and 3. I want to obtain the third one for us and plug it in there as well, and then we'll have a full set and we'll start talking about what to do. Okay, right now we're just doing the math and the algebra to get these laws in place. They all came from this law and those definitions we had earlier. Okay, so the third one, here's a side calculation. So now solve for t in equation 2 and plug into equation 1. So when I solve for t, I get t equals b minus b0 divided by a. And I have to plug this expression in here. That's going to generate a few terms. So let's just do it. We end up with x equals x0 plus b0, and then I have to write b minus b0 divided by a, and then I have to write plus 1/2 a, and then I have to square this thing, v squared minus 2v0 plus v0 squared divided by a squared. And now I have this expression here, I'll call it a star, and I'm going to cut to the chase and write the answer down. Students should solve this to obtain equation 3. Okay. So I'm going to write equation 3 down. What you'll end up with is b squared equals b0 squared plus 2a x minus x0. Yeah, this is the kind of practice you guys should be trying to get, and here's a place I left you to do that. So leave some space in your notes, and you're just going to rearrange this. It's not difficult, and you're going to obtain this. And these are the 3 kinematic equations that we use again and again and again. Okay. So this was all, and to go over this again, the drop chord experiment, that was the physics. And the definition, the kinematic definitions, were the physics as well. Then this last couple of boards was just algebra, okay? Because I just used the definitions and this crucial fact here of constant acceleration, plugged them into the definitions, and now I have these 3 laws of motion that we have to learn how to use. Okay? So the first thing we have to do is, well, we'll send them up to Tom to just work on the lower board. The first thing we have to do is write them down and know what each thing in the what each letter means, what it refers to, and then we're going to apply them to certain situations. We can apply them to motion on a horizontal track. We can talk about cars starting up, slowing down. We can also talk about free fall. When we talk about free fall, we're going to give the acceleration a special name. Okay, so one step at a time. Let's see how we're doing for time in this hour. Yeah, we're getting there. Okay, we have our kinematic formulas. We're doing free fall. Well, we were doing free fall with constant acceleration. What we found was the kinematic equations for constant acceleration. Now it's time to apply them. can learn to graph them. We can learn a lot of things. So the kinematic equations, 1, 2, and 3, one and two describe the time dependence of motion. So 1 and 2, position versus time. And actually, how about I put the 1 right here? That's 1. And equation 2 is velocity versus time. So what do we have here? We have position x. We have x sub 0. So this is what's called the initial position. The position when time is equal to 0. We have v0 is the initial velocity, and a is the constant acceleration. Okay, so position, initial velocity, acceleration. Okay. And in the velocity versus time, we have initial velocity, acceleration. Yeah, and all of these t for time. So you want to know what each of these things means. So I've written that down for you. Position, initial velocity, constant acceleration, time. And we can do various and assorted graphs of this. We'll do the graph. If we do an x of t, a position versus time, there are a lot of possibilities. If the acceleration is 0, then it's just the straight line we have been talking about before. If the position and the initial velocity are both 0, then it would just be 1/2 at squared. It would just be a parabola. Okay. So there are many different examples. You know what I'll do? A equals 0. Then it's just a straight line that we had before. And the other example, A is not equal to 0, comma, all right, but x0, b0 are both equal to 0. And then what do we have? We have just x equals 1/2 at squared. And if t is the variable here, you guys know the thing grows up like a parabola. Okay. So as far as graphing these things, you start to get a feel for what the different expressions mean there. And the graph for velocity versus time, actually we've already done the graph for velocity versus time. Just check your notes on that one. Okay, what we want to do next is relate this to free fall, because we started with free fall, and that's what it's really the one we should tackle first. In your chapter it's different. They tackle free fall at the end, but we started with free fall because it was an interesting phenomenon. So for the law of free fall, and I'll end the lecture with this. So free fall, what we do is we take the kinematic formulas and we say that A is equal to minus G is equal to minus 9.8 meters per second squared. Notice G is a positive number, and I put a minus sign in front of both of these here. So this is free fall when up is positive direction. So if I measure my, if I put my meter stick here, here's 0, here's 1 meter, then up is the positive direction. And then what this means is the acceleration is in the downward direction. Okay. And it turns out the acceleration due to gravity, so here's another note, G equals, or is the acceleration due to gravity, that's what we call it, gravitational acceleration, and it equals 9.8 meters per second squared. Actually, using this formula, you could then discover that number, that it's 9.8 and say not 3, okay? It's 9.8 meters per second squared. And the last thing I'll write up for today is these kinematic equations when we have G equals 9.8 meters per second squared pointing down. So these will be the free fall kinematic equations. Go ahead and write free fall kinematics. And then we'll get a ton of practice with these. So we're just going to plug in A equals minus G. So we'll get X equals X0 E0 T minus 1/2 GT squared B0 minus GT B squared B0 squared minus 2G X minus X0. Okay. These are the case when the positive direction is up and we're doing free fall. So what we'll do next time is a very serious, a very thorough discussion of these three formulas, how to use them to discuss anything you can possibly understand about free fall. So suppose I launch the ball and then I catch it. How long was it in the air? How high did it go? What's the height dependence on the initial speed, how hard I throw it, and so on and so forth. Okay, I don't want to neglect putting up a homework assignment, so let's see if we have any good ideas here. So we're in chapter 2 now, and let's see what we've got for you. Chapter 2, motion in one dimension. That's what we've been talking about. You'll see a lot of these graphs, you'll see all these definitions, and we just want to do a couple of good problems. So this is homework. Chapter 2, and always from the problems at the end of the chapter. Yeah, we can't really do these hard free fall ones, so we'll just do some basic definitions. Good, we've got 1, 2, and 4. 1, 2, 4. And let's see if we've got something else good here. Yeah, I don't want to do the free fall ones until we've worked on them together. So we'll just stick with yeah, we just got some definitions there. Number 6 is good. Number 6 involves some graphing. So 1, 2, 4, and 6. Have a look at those. And next time we meet, next lecture, we're going to analyze these things very thoroughly. Okay, good. See you all next time. Okay.